Hello everyone. So, welcome to the last lecture. So, today we will finish off this course. We will start by reminding you what we were doing in the previous course, previous class. So, in the previous class we were looking at a series of spectroscopic techniques in different energy ranges, right. So, we started by looking at impedance spectroscopy, that is to be done electronically. We said okay, so that gives me what properties I have studied as capacitance and conductance, right. So, these are more sort of electronic properties, they are related to just the electronic levels, which are mostly valence bands and conduction bands, and then the excitations of these electrons, which are in the order of 100 nano electron volts, right, that is less than the thermal energy or so up to gigahertz, right. So, we do those sort of measurements. Then we moved on to more sort of optical measurements. We said we have terahertz spectroscopy or sound based measurements, right. So, mostly I am looking at electromagnetic waves as the inputs. So, if that is terahertz or Raman, then what I am looking at are the phonon spectra, and phonon spectra are related to what is happening in the valence band. Valence band has a lot of bound electrons, right. So, these electrons are responsible for forming the bonds, and these bonds are sort of vibrating. So, I have the ionic polarizability comes because of this bonds vibration, right. So, I have these resonances, the ionic resonances happening at terahertz, and that can be picked up from terahertz spectroscopy. And then so vibrating bonds actually, so if I send in some energy, these bonds vibrate even more, and that is equivalent to an excitation of a phonon to either a real state or an virtual state, and excitation of a phonon to a real state is absorption, and this absorption we can catch using an absorption spectroscopy. But this goes after Sir C.V. Raman, who or the Raman spectroscopy, and he won a Nobel Prize for looking at the vibrational spectroscopy of molecules, right. And then we moved on, and then we said okay, so if we go further deeper into the energy scale, we are actually going further deeper into the energy band diagram, right. So, we start with vacuum level, but we start going deeper. We look at valence band to conduction band transitions, these interband transitions, that is optical spectroscopy. Then we said okay, it is not just absorption, we also have emission spectroscopy. If I absorb, if my electron absorbs energy and then jumps to the conduction band, then so there is when the system de-excites, there is also a photon that comes out, right. So, this is what is called photo emission, or photoluminescence, right. So, we have photoluminescence spectroscopy, right. So, coming out of it is a part of being emission spectroscopy, right. And then we went further down into the valence band, right. So, actually what I so I'll talk about what is XPS today, and then so there is something called UPS, which is also an emission spectroscopy. So, that discussion I have postponed because I will do XPS and UPS together, but nevertheless so I have photo emission spectroscopy. So, I can understand the band gaps, the dynamics of electrons also, right. So, of excited states coming back to de-excited states, right. So I can understand that from photo emission spectroscopy. Now, the point is all these various processes happening at different energy scales are what are contributing to the property of that material, and this property in this case being refractive index or epsilon being the dielectric constant, right. Then if I further go deeper, right, so then I start exciting the core electrons into the valence electrons. These sort of techniques, you have to be able to have energies which are of the order of 100 electron volts or even larger, right. So, 1000 electron volts keVs, then you need X-rays, right. So, X-rays have that much of energy, X-ray photons have that much of energy that can excite an electron from so some core level and put it up in the in an empty shell, and this from here onwards, so we do not really care anymore about the dielectric function at these frequencies, rather we so we get information about the chemistry of the material. Chemistry meaning what is that element, right. So, what is that atom from the core level of which there has been an electron that is excited to the valence shell, and what is the oxidation state of that atom, and so on and so forth. So, you get some bonding information, but at the same time you get the information. You can not just so if I am doing both microscopy, electron microscopy, where I can see these atoms, and also spectroscopy, this absorption spectroscopy together, then I do not just see atoms, but I can also smell these atoms, right, which means that I can know the chemistry of these atoms. Okay. So, so everything that is supposed to be known about the material material you can understand from the absorption spectroscopy, right. So, it's a field in itself, okay. And core level absorption spectroscopy, this is the chemistry is coming from core level absorption spectroscopy. Let me quickly show you, so one of these, so for example, this is what I was talking about, EELs, which is electron energy loss spectroscopy. This is also an absorption spectroscopy based technique where I shine electrons, right, and then I shine electrons at an energy E1 and then I detect electrons at energy E2, right. So, now E1 minus E2 is something which is absorbed by the material, this is what is absorbed by the material. But I just do not, I catch electrons at all different, so I catch electrons at E1, I catch electrons at E2, E3 and so on and so forth. So, I do a frequency scan, right. So, I do an energy scan, right. So, this is a typical absorption spectroscopy, but here my material is absorbing energy from the electrons, incident electrons, not photons, okay. And so you see all these peaks coming at about 5 electron volts, this is coming at about, so all you have all these various absorption processes, right. So, this is analogous of looking at the imaginary part of refractive index as a, or so just the absorption coefficient, right. So, absorption, okay. So, this goes from a range of 0 electron volts all the way up to 35 electron volts, okay. So, I have, and so I keep saying that at about 20 electron volts there is what is called a plasma peak, plasmon oscillation from the valence band, right. So, valence band plasma this is, right. So, all these are the various absorption processes, and from the absorption spectrum I can estimate what my epsilon 1 and epsilon 2 is, because I have Ni, from Ni I can get Nr using Kramer's chronic relations, and so I have Ni and Nr. So, my N is actually Nr plus I Ni, correct, and from here so I just take N square is my epsilon, right. So, I just have to square, so Nr square plus so actually minus Ni square plus Nr2 I Nr Ni, and so this is going to be the imaginary part of epsilon, this is going to be the real part of epsilon, right. So, I can really estimate what epsilon r is and epsilon I is just from Kramer's chronic relations. Once I have the absorption spectra, I can get all these functions as a function of frequency. This is called the dielectric function, right. So, as a function of frequency, epsilon 1 and epsilon 2, epsilon real and epsilon imaginary, okay. So, that is how I understand properties. It is not just enough to understand what is the capacity or what is the dielectric constant of the material only at 0 frequency. I have a complete understanding across all the frequencies, right. So, so at different frequencies different phenomena, different dynamics happen in the material, and everything together conspires to tell me what the epsilon real is and what the epsilon imaginary is, and same thing can be applied to all the other properties that we studied, okay. All right, so that is good. Now, so in any case so I showed you some images in the last class where if I go towards more sort of a core hole, if I create a core hole and excite this electron, so if I create a core hole, right, so I can detect this energy, right, and this energy so of an electron jumping from the core hole into an empty state which is up, that takes some energy from the incident electron or incident X-rays, and that goes as X-ray absorption spectroscopy. So this X-ray absorption spectroscopy or electron energy loss spectroscopy gives me information. So for example, this energy, right, so this delta E, if this delta E is about 450 electron volts or 450 to 470 electron volts, there is a range because this is a band, right, so it can excite to anywhere in the band, right. So then I say that what I have is titanium atom, okay. Then based on the exact positions of the peaks that I am seeing, based on the exact peak positions, right. So, I can also say whether it is Ti4 plus or Ti3 plus, right, or Ti2 plus, whatever is the oxidation state of titanium. Okay. So I just so I have complete information about the chemistry of the materials by doing this core level spectroscopy. Okay. Now there is there are two more let us say features, I mean, so two more ways in which you can do core level spectroscopy. One is called so let's talk about what is the analog of emission spectroscopy. XAS and EELs are absorption spectroscopies, right. So what is the analogous emission spectroscopy or luminescence spectroscopy, right. So in some sense, if I shine electrons of energy E1 or if I shine X-rays of energy h nu, this is X-rays, these are electrons, right. So electrons interact with my material, right. So how are they interacting with my material? So there is a core level. So this is the interaction. There is a core level. There are some empty levels in the valence band. So the electron from the core level excites, right. So this is the excited state. So I create a core hole. So this is a core hole, and there is an excited electron which has gone here. This is an excited electron. Okay. All right. So this is the excited state. Then it de-excites. When it de-excites, right. So this electron is here now. So this is an excited state, right. So then I have a core hole here, but there are, let us say, other core levels, right. So and this is the excited level. So there are going to be now transitions. So this is a hole, right. So these are all electrons. So here I have filled electrons, right. Here also I have filled electrons, and here also there is some excited filled electrons. So this electron starts coming here, this electron starts coming here, this electron starts coming here, and so on and so forth, and everything, all these core level de-excitations, they emit X-rays, they emit characteristic X-rays. Okay. So that is also a fingerprinting technique, right. So once I see X-rays that are emitted at certain energy, right. So for example, this is what is called K shell, this is L shell, this is M shell, right. So if I look at X-rays from L to K transition, emits an X-ray of something like 3.5 kilo electron volts, right. So then I know which element it is. This fingerprints the elements. Okay. But this is emission spectroscopy. I am looking at the de-excitation, right. So I am looking at the de-excitation. But here de-excitation also gives you photons, but these photons are X-rays. In photoluminescence, de-excitation was giving you photons, but these photons are actually are visible light, right. So that is just between the valence band and conduction band, right. So the transition is just between valence band and conduction band. Here in core level de-excitation, the photons are actually X-rays, right. So their energies are much larger, they are kilo electron volt energies, and this is also a chemistry fingerprinting technique. And this technique, if I use electrons, right. So this is called EDS, or energy dispersive spectroscopy. Okay. And this is a very standard technique used in all SEMs and TEMs, right. So to understand the chemistry of the materials, and if I do this with X-rays, then this is called X-ray fluorescence, right. So XRF, or X-ray fluorescence. The essence of the technique is the same. So I understand the chemistry, right. If I use it with electrons and then look at the X-rays that come out, right. So it is an emission spectroscopy. So then that is X-ray fluorescence. If I do it with electrons, then if I do it with X-rays, it is X-ray fluorescence. If I do it with electrons, it is called EDS, or energy dispersive spectroscopy. Okay. Now there is another emission spectroscopy, right. So if I shine again light of h nu, and this light is X-rays, let us say. Okay. So So, I have valence band, I have empty band here, and there are all these core levels, right. So, now I shine X-rays, this X-ray will create a core hole here, but this if this electron is completely knocked out of the material, right. So, that also can happen, right. So, this is the vacuum level, and above vacuum level, if I knock off an electron above vacuum level, that means this electron is completely gone out of the material, right. So, this core hole is created, but electron disappears from the material, right, which means it has gone into the vacuum level, right. So, the energy that this electron so needs to get out of the vacuum level is this much, right. So, H so this is the energy that the electron needs to get out of the vacuum level, right. Now, what is this? This is so can electrons do that? Can they get out of the material? Indeed they can, right. That depends on what is the work function and all these things, right. So, that Albert Einstein had said this is nothing but this is called a photoelectric effect. So, I shine electrons and I get I shine photons and I get electrons out, and in this case the photons are X-rays, right. Now, using this technique, right, so I can actually measure the energy of the electron that comes out, right, and the energy of the electron, the kinetic energy of the electron that comes out is actually going to be so vacuum level minus the core energy level, that is this E, right, and so this is the energy that the X-rays need to spend to knock off the electron, right. So, create the photoelectron, and so since photoelectron has some more kinetic energy, that is h nu, right. So, all the energy is actually coming from the X-rays, the incident X-rays, right. So, using this so I can actually calculate what is called the binding energy, right. So, I can calculate the binding energy of the electron just by measuring its kinetic energy. So, when it was in its core level, right. So, what was the binding energy? Okay. So, this is also an emission spectroscopy, because here I shine X-rays and I am emitting out photoelectrons, right. So, this is also emission spectroscopy, where I am but so I am emitting photoelectrons, in that sense it is an emission spectroscopy, but I am still observing the excited state. I am not looking at the de-excitation, right. I am still, the photoelectron is a consequence of excitation of an electron. So, I have just removed the electron from a core level and put it outside. Okay. So, as a result so it is a I am looking at the excited state, but I am emitting a photoelectron. I am not just looking at the loss of the incident photon, right. So, it is slightly different. So, we give it a special name, we call it photoelectric or electric effect or photoelectric spectroscopy, PES. And if I do it with X-rays, I call it as XPS, X-ray photoelectronic spectroscopy. Okay. Photoelectronic, not electric. Okay. So, X-ray photoelectronic spectroscopy, right. Now, what does X-ray photoelectronic spectroscopy give me? It gives me again this gives me the chemistry, just like XAS, right. So, this also gives me the chemistry of materials, and in some sense so I am actually understanding so if I knock off this electron so I can knock off I can knock off any electron, right. So, these are electrons in the filled states, these are the core levels, right. So, if I knock off this electron so it gives me the density of states of the valence band, right. If I knock off this electron, it gives me the density of states of this core level, and so on and so forth, right. So, this is actually giving me the density of states. It is a very powerful technique which can give me the density of states of occupied electrons, okay. Whereas, the absorption spectroscopy works by exciting an electron from here to these empty levels, right. So, it is actually occupying the unoccupied states, and so absorption spectroscopy gives me density of states of unoccupied electrons, unoccupied electron states. Okay. So, that is the difference between PES and absorption, X-ray absorption spectroscopy. Okay. So, so in other words, so if I have to knock off just a valence electron, right, so I do not need to give X-rays, right. So, if I have to knock off valence electrons, UV light is enough or visible light is enough, right. So, it is just the work function, right. So, this is what is called the work function then, right. So, I have to just go above the work function and just UV light or visible light is enough, and this comes under the purview of it is also a photoelectronic spectroscopy or UPS, ultraviolet photoelectronic spectroscopy. Now, ultraviolet photoelectronic spectroscopy is very powerful to give me information about not just the band structure, but the band structure in what is called the energy versus K diagrams, right. So, energy as well as in momentum, right. So, we will not go into details of this. This is a solid state physics course, a complete course on solid state physics, right. But just like you have band structures in energy versus space, right, if I take the Fourier transform of space, that is reciprocal space, or that becomes the wave vector or the momentum of particles, and so I can have band structure in terms of energy of the electron versus the momentum of the electron, right. So, or the K, the wave vector of the electron, right. So, these are so you may have seen band structures which are parabolic in nature for free electrons, and for the bands in K space look somewhat like this, right. So, this is going to be the valence band, this is going to be the conduction band, and then you have a band gap, right. So, these are called EK diagrams. Okay. Sorry, this is K, this is E. These are called EK band diagrams. So, you can use these sort of techniques, UPS, right. So, to get to these EK band diagrams, right. In fact, this is called angle resolved photoelectronic spectroscopy. Will allow you to use EK diagrams. Okay. So, I will not go into details of it, but I would urge you to actually, if you are interested in spectroscopy, you can actually give a cursory reading through Wikipedia or some basic source to understand what this angle resolved spectroscopy is, angle resolved PES is. It is a very cool, neat technique to get a complete information about the band structure of your valence band and conduction band as a function of K. Okay. Okay. So, with that, let us stop here. So, that is the end of spectroscopy. So, we have gone all the way from the top of the valence band, the first electron, right. So, the least energetic electron, right. So, that can have an excitation, a very low energy excitation, all the way up to the core electron, whose excitation will take energies, right. So, energies of the order of 1000 electron volts and larger, right. So, and then we said that so what you are measuring as a property is some form of excitation of these electrons, right. So, that is basically that is what we are saying. So, you provide a wave, an incident wave, right. The property of the material, we said thermodynamically saying I have a free energy curve, right. So, and then I actually excite the system, right. So, this is the free energy, Helmholtz free energy versus some sort of a reaction coordinate order parameter. I excite the system a bit by taking it away from the equilibrium, right. So, this is an excited state. This is what I studied thermodynamically, but how am I creating this excited state? I am creating this excited state by giving some energy in the form of incident photon or incident electron, right, incident particle, and that energy is taken away by the system. That creates in the electronic structure or the vibrational structure of the materials, it creates some excitations, right. Now, this excitation can be just virtual, right. So, which means it gets excited and then comes back to equilibrium without losing any energy, right. So, there is no real state there. Now, those turn out to be your equilibrium, or those turn out to be your the properties that ensue out of these excitations, the virtual excitations are equilibrium properties, whereas the properties that ensue out of real excitations, where there is a real absorption that happens, right. So, in this quantum mechanical framework are your dissipative properties, right. So, this joins this spectroscopy actually joins the dissipation that we studied in third part of the course and conservative properties that we studied in the second part of the course, okay. But it also adds in the dynamics, right. So, everything needs to be looked at as a function of frequency, right. The first 3 parts we were sort of looking at everything almost at 0 frequency, we were not really so we look at static, so in some sense we were just looking at static properties, right. So, I said dissipation means there should be a flux and there should be a force, but flux and force meaning if I am doing a DC experiment, if I have electric field which is constant, then if there is a flow of current, then I say that okay, so that is resistance, that is dissipation, right. But if electric field itself is varying at some gigahertz frequency, there will always be flow of current, right. Then you have to look at the dynamics, how is this current flowing, is this flowing in phase or out of phase. It will flow in phase if current is in phase with electric field, if the corresponding excitation that I have in the quantum mechanical picture is a real excitation, right. But current will be out of phase if the corresponding excitation is from this valence band into the band gap, that is a virtual excitation, right. So, so that is how you reconcile all these things. So, classically you can study it, quantum mechanically you can study it, applying frequency is the same as applying energy, right. So, you can reconcile all these things and then understand how to measure these properties. Okay. Now, okay, so that is the end of the course, but I want to leave you with some sort of tying the threads of what we have started with and what we have ended with, right. Now, if I go back to the first lecture, I said we should be able to design electronic, electromechanical and optical devices, right. Now, are we in a stage to design? Okay. So, that is the let's be honest. Okay. So, now okay, if I ask you to design some sort of an electromechanical material, yeah, I have some idea as to okay, so what I need in this material is huge fluctuations. I gave you a design problem of putting graphene in between these layers of different compositions and heterostructures of different compositions and making thin films, right. But I did not specifically say this is how you design this material, this is how you design this material, right. So, I gave you 1 or 2 examples, but the idea is this course should equip you to do that, right. So, so now I understand if I have to design a material of a certain property, so first question I will ask is that property in what frequency range, okay. Now, what are the different dynamics that are playing a part in that material in that frequency range? How do I understand this dynamics? First I have to understand what is happening in this material, right. I understand these dynamics by looking at the spectroscopic techniques, right. Then I understand what is lossy, what is non-lossy, okay. And then then I understand okay, so there is a transition here from a defect state to an non-defect state, right. So, something like that. Or in NV centers, right. So, a diamond for example has an electron transition only at 6 electron volts, right. So, interband transitions at 6 electron volts. But if I put a defect engineer diamond, I put an NV center in diamond, then I am creating these 2 states that those are qubits, right. So, I have engineered a qubit in diamond by putting in defects, okay. So, that is the engineering part, right. So, that is how I design my materials. If I understand this course properly, if I understand how properties come out, right, then I should be able to use my intuition, right. So, and some sort of hand waviness, model it later and then design materials of interesting properties, right. So, if I need a material which is a very good nonlinear optical material which has very high so if I shine light at frequency omega, I should get out light at frequency 2 omega, right. So, then I say that okay, that's second harmonic generation. What I am really looking at is to enhance the second harmonic generation, the property of second harmonic generation. So, what do? I look at, then I go back to my symmetry principles. I look at materials that do not have inversion symmetry, but not just that, right. So, I look at the thermodynamics to see so how this chi is going to be enhanced. I did not really tell you how nonlinear properties such as chi will be enhanced, but that is, since it is a thermodynamic property, that will also be related to some sort of fluctuations of fields or whatever, right. So, statistically. So, I will go back and try to understand that, right. So, this is something that you can do beyond the course, try to understand it and then see which are these materials, right. So, or how can I design such a material where fluctuations of so some quadrupole moments are the highest, right. So, not the dipole moments, but this time it goes to more sort of quadrupole moments, right, and so on and so forth, right. So, this course, right, so it gives you the basic understanding of how to, in a generalized way try to understand properties, and these properties we classified them as conservative, dissipative, but then we said the dynamics actually combines both these conservative and dissipative properties. It is one and the same of the same coin. We said how to understand these dynamics from spectroscopic tools. So it equips you with, so if I give you a black box material, you can understand, so which property, whatever property you are looking for, how do I first measure these properties, and once I measure these properties, what are the ensuing dynamics that are creating these properties, and then I have to treat these dynamics, right. So I should change the phonon spectrum, let us say, right. How can I, so let us say there is some sort of a Raman excitation to a real state. Now I have to remove that real state. Phonon should not be exciting to that state, right. I want to remove that absorption. My material design involves that I have to remove that absorption. Then I will see how can I remove that phonon state that exists at some gigahertz frequency, right. So I create something called a phononic crystal, right. So that is where the engineering comes, right, and then I can remove that phonon state. If a phonon state exists, how can I remove it? By creating some artificial structures, right. So then the problem definition becomes clear. That phonon state exists, there is an absorption to that state, I want to get rid of that absorption. If I want to get rid of that absorption, I will create some sort of an artificial lattice, right. So a phononic called phononic crystal, and so then I have to study a bit more about phononic crystals, but that is capable of inducing some sort of a band gap or removing that real state, right. So it will make it a virtual state. Then I do not have to worry about any sort of dissipation or absorption that happens to that state, right. So this is how I am going to use, so the example that I gave right now is again is in terms of a qubit, right. So qubit, for example, so qubit is, let us say, one the qubit in NV centers, let us say, right. So that's an electron, so that's an electron that can exist in two states, right. But these electrons I said that this electron cannot interact with any other electrons in diamond, because these other electrons are very far away, right. So in energy scale, so there is no real interaction between this electron which is at the middle of the band gap versus the other electron. So my qubit does not have any electrons with any interactions with the other electrons, but it can interact with phonons, right, and it will interact with phonons at a certain frequency, right. Now if my qubit is interacting with phonon, it will forget that it is a qubit, right. So by the time I measure this qubit, it would have forgotten the information that I fed into it initially. So I cannot do any quantum computation if the qubit is interacting with phonon and sort of decohering by itself, right. So I have to get rid of these phonon frequencies where qubit is interacting, meaning, so it gives its energy to phonon, and phonon has a real state where it can get excited to, right. So I understand what that real state that phonon can get excited to through some sort of Raman spectroscopy. Then I say, okay, so this is interacting, but I have to increase the coherence time of this qubit so that I can do some quantum computation. So what do? I have to get rid of these phonon modes that are interacting with this qubit. How do I do that? Then I create these artificial structures called phononic crystals or whatever they are to actually get rid of that mode, right. So it's a logical progression that I go through in designing my materials, right, using these basic principles. Okay, so I want you to look at this course in that way, right. So these are the basic principles that I will use, and I go on to, so if I understand them with heart, right. So then I should be able to intuitively say, okay, so logically progress and then say, okay, so ideally these are the ingredients that this material should have given the property that I want, and then I go and then say, okay, so then how do I go about making these things, right. So in case of the qubit example, I said the making part becomes difficult, then I have to make a phononic crystal, that is not a trivial task, okay. So and so on and so forth. In case of enhancing the electromechanical coefficient, I said, okay, so this thin film, right. So if you go back to one of the earlier lectures, so I can make thin films of different compositions which have different phase transition temperatures, but so they will start diffusing, right. So if I have different compositions, then these materials will start diffusing into each other, and by the time I cycle it, it will not be stable. So I put these graphene layers in between so that there is no diffusion, right. So that is my material design. So once I have designed the material, then I go to a growth chamber and start growing this material and see whether what I have grown is what I have designed to start with, right. Now if that does not come up, so as you have predicted initially, then you do a feedback, right. So you see what is wrong and how to improve on that, and so on and so forth, right. So that is how materials research progresses in general. and so that's what I want to get give you a feel for. Okay. So I hope in this course you then understand some concepts could be tough for some of you, some concepts can be easy for some of you depending on your background, but I urge that you go back, read the assignments, look at the notes, and then if so I'll be available over email, or so we can have these discussion sessions, NPTEL discussion sessions, in which you can ask your questions, and so it's okay if you understand 70% of the course, right. So let's put it that way, not 100% of the course. Okay. And so with that so you can go back to the course syllabus and see that we have more or less covered everything, right. So and in a very coherent manner. So then so with that, let me say goodbye to you, and that will be the end of this course. Thank you very much, and I hope you enjoy the course.